My name is Pablo, and I'm going to present my work for you today. So the first thing that I want to say is that I changed a little the title of the presentation to make it more clear. So the title now is A Simple Setup to Measure the G1 of T of atoms or other quantum two-level systems. So the idea of this work is to revisit taking a topic that was very famous during the 60s, which is the resonance spectrum of an atom or other two-level system. So when we drive an atom, for example, with low intensity light, we know that the spectrum that's going to be scattered by this atom is trivial. It's going to be just the spectrum equal to the light that is excited by atom. But when I drive this atom in a strong driving limit, the spectrum becomes much more complex and much more interesting with the three-peak structure called moral spectrum. So this three-peak structure was seen several times for several different systems. At first, it was seen by atomic beams, where I have an atomic beam and perpendicular to the direction of the propagation, I excited collect the light. It was also seen by quantum dots and more recently by molecules. So the similarities between these three examples that I'm showing here is that in these three cases, the spectrum was programmed using a Faraday-Behold cavity. So, which is actually the most usual because I can use this Faraday-Behold cavity to just filter the frequency and then measure the spectrum, measure how much power I have for each frequency. And then, much more recently, the model triplet was seen by both atoms. And here, instead of measuring the spectrum itself, what was measured was the G1 function of the light emitted by the atoms using this heterodyne technique. And then, by calculating the Fourier transform of this G1 function, I can obtain the spectrum itself. So, the idea of the work that I'm going to present is going this direction. So we want to use this setup that we have been using in our lab that is called mirror system scattering to measure the G1 of the atoms and then by its equivalent to measure the spectrum of these lights. So to start about how this setup works, the idea is that I have an atom or an atomic cloud in the front of the mirror, and I'm going to drive these atoms using a laser beam. And then what is important here is that the atoms are not going to be driven only by the laser impinging on them, but also by the reflection. And then in the direction theta, where I collect the light in the far field, this light is going to be composed by two different scatterings, which is the scattering that is going to happen directly in the direction theta, and the scattering that is going first in the direction of the mirror and then to the direction theta itself. So in the very far field, I'm going to have the interference of these two lights, and as a result, the interference pattern in my far field is going to be composed by this green fringe shape. So they have an envelope that is given by some parameters related to the size of the cloud and the distance to the mirror. But what is important is that the contrast of these fringes is going to be what I'm going to use to program my G1 itself. This is not something new. It happens for several interferometers where the visibility of the fringe is somehow proportional to the G1 function of the light. So once I have the system, how I actually do assemble it in an experiment, to construct it, you need just a few elementals. You need a beam splitter, one mirror, 3 lenses, and a CCD camera. And the idea is that I have my laser that's going to impinge on my atoms. Then, since I'm talking about that scattering, I need a beam splitter to collect the light that is better reflected. This lens is just to make I don't need to properly observe the very far field. I can make a conjugation and then observe the strings in my CCD camera. And here I have this mount that I call virtual mirror, and it's important to reflect the light back, so it's the other direction of reflection. And the importance of this virtual mirror setup for our experiment is because first, I don't need to put the mirror very close to my cloud, so I can put the mirror far away. And there is another two important things, which is first, since I have this virtual mirror mount, my mirror can be very far away from my cloud, so I can actually create a big time difference between these two light beams, and this will produce a time difference to measure my G1 itself. And this virtual mirror setup is also important because since I'm throwing like my atoms with an angle with respect to the mirror, the path that goes to the real mirror and come back are going to be separated, and then I can insert a wave plate in between this path, and in this way I can control the polarization independently of the lights that is scattered direction in my detection direction, and the lights that is first scattered in the direction of the mirror and then to my detection direction. So once I have this wave plate to control my polarization, I can control, for example, how the light interferes in the region of the atoms. In this way, I can produce, for example, a standing wave where I have just one polarization and the intensity is modulated. And I can, so in this case, I'm actually not doing anything with my wave plate, but if I rotate it, I can make the light, the polarization of it being perpendicular as it passes through the wave plate. And then I can have a wave that it has constant intensity, but it has a polarization that changes as a function of the atoms. So in this case, what I'm going to have is that since all the atoms, independent of the distance for them to the mirror, they are going to see the same intensity, which means they are going to scatter the same G1. So they are going to, for atom in all distances, I have the same spectrum. And so I can use this to measure the G1 of a macroscopic cloud. The only difference is that as a function of the position, they are going to scatter light with different factors, with different multiplicative factors. But once I then do the calculation, instead of using just one atom in front of a mirror, but I extend the cloud, for example, a Gaussian cloud, what I have is that depending on the angle of my wave plate with respect to the polarization, I have different fringes. But for the case when the polarization becomes perpendicular, which is the angle P over 4, I have that the oscillation of the contrast is exactly equal to my G1 function. So in this way I can then measure the G1 and measure the spectrum of the light that is scattered by these atoms. So just to finish, I talked about the case when I have this wave plate rotating by 90 degrees my polarization. For when the wave plate is somewhere in between, what I have is a more complex distribution of intensity and polarizations. And this case, it's exposed in a poster in section for those who want to know what happened. But just to tell you, what happened is that for any angle of my wave plate, I have that the contrast of my fringes are independent. So somehow I have an interferometer that is independent of the polarization. So to conclude, we have this setup that can easily be used to measure the G1 function of the light scattered by atoms or other quantum two-level systems. What is interesting in this setup is that I don't need a very high precision positioning of my mirror, because it depends on the line width that I'm going to measure, but it's going to be something like a few millimeters or a few meters. And another thing interesting in the system is that I also don't need fast photodetectors to make these heterodyne measurements, as I just showed you. And just to conclude, this setup was already used by us to measure the coherence of light scattered by cold atoms, and also by another group to measure the coherence of light scattered by hot atoms in hot vapor. So it's a very simple setup, but it has been used to measure many things, and once we add also more visible, that somehow it's going to be more interesting. So that's it. Thank you.
It's a quick presentation.
Yeah, it was. I talked too fast.
No, it was understandable. It took short. Questions? How? Okay, I do have one. So you talked about peripheral cavities. You measure the spectrum of your light, right? Are you interested only in the intensity over all wavelengths, or really in the noise spectrum of the light? I mean, are you measuring short noise or something like that?
So for these measurements, we actually need to integrate the light scattered by the atoms by a long time. So if you have fluctuations, they are going to disappear in the image. So it's not very easy to do this using this setup.
Okay, so with the information from the gravity, you actually take the interference pattern directly from the...
Yes, so actually, so this is actually a real image of what we see in the canvas, but then we have to do the same measurement several times to overcome the noise.
So for the fabric, you get to the spectrum.
Yes.
So for the fabric, you get to the spectrum when you scan the mirror. So you get the transition. So here you get the Fourier transform of the spectrum, which is the G1. So actually, you don't get the G1, you get the G1 tilde, which is the G1 in the rotating wave approximation, which is loosely dependent on tau. This is why it's not. So when you measure G1 of light, normally you need to scan your mirror with sub-micrometer precision. Here you don't need this. You can make centimeter scale points and you can get this. So these are for the easiest things. So they are hard details to implement this. Alignment is a little simple, so it's not the easiest thing to measure G1 in some ways, but it's the easiest technologically in other ways as well.
Other questions? No? So I declare the end of the session. Thank you, Pablo, and all the speakers.